Hello students, welcome to Microprocessors course content. I am Nazmus Saqib, lecturer of BRAC University. I am one of the instructors of this course. In this lecture, I am going to introduce Intel 8086 microprocessor. In this part, I am going to describe memory partition and registers of Intel 8086. Here are some reference books that will be helpful for better understanding and practicing. Intel 8086. The microprocessor 8086 is considered the basic processor for Intel x86 family, and it was invented in 1978. You may have questioned, in this era of 2020 where Core i5, Core i7 processors are available, why are we telling about a processor which is old and was invented in 1978, right? We all know to write a full paragraph, at first we have to learn to write a single line. Understanding a basic processor will help you to learn about newer developed processors. 8086 has a 20-bit address bus and a 16-bit data bus. Here 16-bit data bus means it can read and write 8 or 16 bits data at a time. From your previous lectures, you all know about the functionality of data bus and address bus. X86 has a 20-bit address bus, and with 20-bit address lines, it can address up to 2 to the power 20 bytes. This will amount to 1048576 bytes, that is 1 megabyte. Here 2 to the power 20, where 20 bits means 5 hexadecimal. Let me give an example first. Here is a hexadecimal value, that is 38A41 hexa. I hope you all know how to convert hexa to binary digits. Okay? So here is the binary representation of this hexadecimal value. That means 3 means 01011, 8 means 1000, A means 1010, etc. So here we can easily see there are 20 bits binary digits for 5 hexadecimal digits. So that is 20 bits to 5 hexadecimal, right? And we all know by these 5 hexadecimal digits, the lowest number can be represented is 00000, and the highest value can be represented is FFFFF, because they are all consist of 5 hexadecimal digits. Again, we all know 8086 has a data bus that is of 16 bits, that can carry 16 bits of data, right? The 16 bits means 4 hexadecimal. 1 hexadecimal means 4 bits, so 4 hexadecimal means 16 bits, right? And it can address up to 2 to the power 16, that means 64 kilobytes. 64 kilobytes. And we all know by these 4 hexadecimal, the lowest value can be represented is 400000, and the highest value can be represented is 4FFFFF, right? Okay. Now, do a simple division. Divide this 1 megabyte memory by this 64 kilobytes. Okay, you will get a result of 16, right? Okay. So in microprocessor 8086, total of 16 64 kilobyte segments can be positioned within this 1 megabyte address space, right? Here is a graphical view. This is 00000, the lowest value can be represented by 5 hexadecimal, and this is FFFFF, the highest value can be represented by 5 hexadecimal. And here we can, this is a 1 megabyte address space of 8086 total, right? And you can easily see this 1 megabyte address space is divided up to 16 partitions. 16 partitions. This is number 1, this is number 2, this is number 2, and this is number 16. So there are 16 partitions, and all these 16 partitions are called segments, right? Okay. Each segment has a starting address. Starting address means where the segment starts. You all know now there are 16 total segments, right? And each segment is of 64 kilobyte of size. That means, suppose this is segment 0. This box is segment 0. its size is 64 kilobyte. This is segment 1. It is also of 64 kilobyte. This is segment 7. It is also of 64 kilobyte. And the last segment, that is also of 64 kilobytes. So there is 16 segments of 64 kilobytes that make up to 1 megabyte memory space, right? Okay. Here we can see this segment 00000 is the starting address of segment 0. 1000 is the starting location of segment 1. 9000 is the starting location of segment 9. And from 00000 to 1000, so there are 64 kilobyte of memory space. Here, 64 kilobyte of memory space. Here is also 500 to 600. There is also 64 kilobyte of memory space. Okay. So we all know now, for each segment, there will be a starting address and there will be 64 kilobyte consecutive memory locations. There will be 64 kilobyte consecutive memory locations within each segment. So what is segmentation? Why we have divided a full memory space into different segments, right? Segmentation is the process in which the main memory of the computer is logically divided into different segments, and each segment has its own base address, right? This is the memory of 8086 processor, and the processor is the whole memory is divided into 16 segments, and each 16 segments has its own starting address. Okay. Okay. Now let me give an example for a clear understanding. Just think this box is one of those 16 segments. That means its size is also 64 kilobytes, right? And this partition, you may say, contiguous memory locations within this 64 kilobyte segment. Okay. This segment must have a segment number, or you may say starting address, and this is the starting address or base address, A4FB, that is of 16 bits. That means 4 hexadigits. This base address can also be said as segment number. But one thing, 16 bits. Why? Because we know 8086 has 16-bit data bus, so it can carry a value that consists of 16 binary digits, right? But you may have confusion. In previous figure, you have seen this 5 hexadigits, that means 20 bits location, and now you are seeing 16 bits address. Why, right? Let me give an explanation for this. 8086 microprocessors 16-bit data bus can carry 16 bits, but the memory location is of 20 bits. So we have to convert this 16-bit location, 16-bit address into 20-bit location. But how? Simple. By appending a hexadecimal 0. The hexadecimal 0 means 4 binary zeros at the end of this segment number or base address. For our segment, the base address was A4FB, this 4 hexadigits, and at the end we have appended a 0 to make it 5 hexadigits. That means 20 bits. Here is the binary representation of 20 bits starting location address, right? Now get back to this figure. Let's just think CPU wants to access this memory location for read or write operation. But how this location can be accessed within this segment? For this segment, we already know the base address, that is of 16 bits, and the starting location, that is of 20 bits. Somehow, if we can get the distance from this starting location to this memory location, we can easily access this location. And the distance from the beginning to this particular location within this segment is called offset. That is of also 16 bits, 4872, 16 bits offset, right? Okay. Now we have our base address, we have our starting memory location, we have our offset. So simply we can do this operation. That means that is our starting location, that is our offset. Starting location is of 20 bits, offset is of 16 bits, And if we add this, we can get A9822, that is of 20 bits, which is the memory location of this, right? So we can easily get a memory address of memory location if we know the base address and the offset. But one thing, what should be the range of a 16-bit offset? And why the offset is 16 bits? Simple answer, because the data bus of 8086 can carry 16 bits, right? So the offset must be of 16 bits. And we know 16 bits means 4 hexadigits. So the lowest value of offset can be 0000, and the highest value of offset can be FFFF, right? So for this segment, the lowest offset should be A4FB plus 0000. That means A4FB 0. And the highest address, that means this location, should be A4FB plus FFFF. That means B4FAF. This is the highest address for this particular segment, right? So from this figure, we know the base address is A4FB, that is of 16 bits. Here is an offset that is of 16 bits to address this particular location. And the offset can be ranged from 0000 to FFFF. So if we add the base address, that means this location, and the highest offset, that is FFFF, to this base address, this one, we can get B4FAF, that is the highest location of this particular segment. Here, a memory location may be specified by a segment number and an offset. This is the notation of memory address representation of 8086 microprocessor. That is, first one is segment number, then a colon, then another number, that is offset, right? These values are called logical address, and from this calculation we get the physical address. That means this is a physical address. A9822 is a physical address. A4AB0 is also a physical address. This is the physical address of the starting location, and this is a particular location that CPU want to access. But what is this physical address and logical address, right? Logical address is the address that is generated by CPU itself in perspective of a program. CPU knows to which location it has to access for data or instruction read and write, right? So CPU generates this address by itself. This address is generated by CPU itself. So these are called logical address. But this address is calculated by those logical addresses. Okay. Whereas the physical address is a location that exists in the memory unit. This is a memory, and these are physical address, that is of 5 hexadigits, that is of 20 bits. CPU does not know these addresses. CPU only know this logical address. Suppose 8000 is segment number, FFFF is offset, right? These are logical addresses. CPU only knows these values, but this is a physical address. CPU does not know this. It is an identifier within the memory, but not in the CPU. So these are the basic differences between physical address and logical address. Then type of segmentation. There are two types of segmentation possible, that is overlapping segmentation and non-overlapping segmentation. What are those? Here is a figure. We all know a segment starts at a particular address, that is base address, and its maximum size can go up to 64 kilobytes, right? But if any other segment starts along with this 64 kilobytes location of the first segment, then the two are said to be overlapping segments. In this figure, segment 0 starts at 00000 location and after 64 kilobyte memory space, it ends at 0FFFF location. But in this figure, you can easily see the segment 1 starts at 00010. Segment 2 starts at 00020. That is the range declared by 64 kilobyte of segment 0. So Here segment 0, segment 1, segment 2 are said to be overlapped segments. And there is another one that is non-overlapped segment. A segment that starts at a particular address and its maximum size is 64 kilobytes, right? But if another segment starts before or after the 64 kilobytes location of the first segment, then the two segments are said to be non-overlapped segment. Just assume a scenario, if in this figure, segment 0 starts at 0000 and segment 0 ends at 0FFFF. But if segment 1 does not start at this location, but instead of it starts at 1000 location, that is after the 64 kilobytes location of segment 0, then there will be no overlapping. So they will be called non-overlapped segments. Okay. You should notice one thing. A physical address can have different logical address. 0001F is a physical address. It consists of 5 hexadigits, right? So it is an identifier of memory, not for CPU. Here, segment 0 and segment 1 is overlapped, and this physical address is within the memory locations of both segment 0 and segment 1. So this can be accessed by both segments. For segment 0, the base address is 0000, the upper 4 hexadigits, not the last one. It is appended one, right? And the offset is 001F to access this physical address or this memory location 0001F. But in case of segment 1, the base address is 0001, this upper 4 hexadigits, and the offset is 000F. If you add 0001 and 000F, you will get this 0001F physical address. So for a particular physical address, it may have different logical addresses in case of overlapped segments.